Welcome! Today, we'll be exploring a fascinating problem titled Queries on Number of Points Inside a Circle. This problem challenges us to determine how many points lie within specified circular regions. Along the way, we'll break down the problem, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, you are tasked with determining how many points lie inside a series of circles. You're given two main inputs. The first is an array called points, where each element represents the coordinates x_i, y_i of a point on a 2D plane. It's worth noting that multiple points can share the same coordinates. The second input is an array called queries. Each query is defined by three values, x_j, y_j, r_j, which represent a circle with its center at x_j, y_j, and a radius of r_j. The goal is to compute, for each query, the number of points that fall inside its circle. Importantly, points that lie exactly on the circle's border are also considered inside. Finally, you will return an array answer, where each value corresponds to the number of points inside the circle for that specific query. To make this clearer, let's look at an example. Suppose the input points is 1, 3, 3, 3, 5, 3, 2, 2, and the queries are 2, 3, 1, 4, 3, 1, 1, 1, 2. The output in this case would be 3, 2, 2. For the first query, the circle is centered at 2, 3, with a radius of 1. The points 1, 3, 3, 3, and 2, 2 all lie inside or on the border of this circle, giving a total of 3. For the second query, the circle is centered at 4, 3, with a radius of 1. Here, the points 3, 3, and 5, 3 are inside or on the border, so the total is 2. For the third query, the circle is centered at 1, 1, with a radius of 2. The points 1, 3, and 2, 2 lie inside or on the border, resulting in another total of 2. This step-by-step breakdown helps illustrate how the output answer is derived. Here's another example to clarify further. Imagine the points are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and the queries are 1, 1, 2, 2, 2, 2, 4, 4, 1. This time, the output will be 2, 3, 1. For the first query, the circle is centered at 1, 1, with a radius of 2, and the points 1, 1, and 2, 2 are inside or on the border, so the count is 2. For the second query, the circle is centered at 2, 2, with a radius of 2. This circle includes the points 1, 1, 2, 2, and 3, 3, giving a total of 3. Finally, for the third query, the circle is centered at 4, 4, with a radius of 1. Only the point 4, 4 is inside or on the border, so the total is 1. These examples highlight how the circles and points interact to produce the output. Now let's consider some constraints and edge cases to keep in mind when solving this problem. The number of points in queries can go up to 500, and all coordinates and radii are integers. The values for x_i, y_i, x_j, and y_j can range from -5,000 to 5,000, while the radius r_j will be between 1 and 5,000. Edge cases include scenarios where no points fall inside a circle, resulting in a count of 0, or where a circle's radius is so large that all points are enclosed. Additionally, points lying exactly on the circle's circumference are considered inside, which is important to account for. Overlapping circles in the queries don't interfere with each other since each query is processed independently. Finally, for circles with very small radii, only points close to or at the center will be included. These considerations will help ensure your solution handles all possible inputs correctly. To approach this problem, the most straightforward method is the brute force approach. The intuition behind this is simple. For every query, we check how many points lie inside the corresponding circle. For a given query, x_j, y_j, r_j, the squared distance from a point, x_i, y_i, to the circle's center, x_j, y_j, is calculated using the formula, x_i, x_j, caret 2 plus, y_i, y_j, caret 2. If this squared distance is less than or equal to r_j caret 2, the point lies within the circle. By repeating this process for all the queries, we can determine the results. However, this approach requires iterating through all points for every query. This means that if there are n points and m queries, the time complexity becomes O, m asterisk n. On the other hand, the space complexity is O, 1, as we do not require any additional storage beyond the basic variables. The main drawback of this approach is its inefficiency for large datasets, especially as both n and m approach their upper limits of around 10,000. To address this, we consider an optimized approach that incorporates pre-processing. Here, the idea is to pre-compute the squared distances for all points relative to the origin. For each query, we can then shift the circle's center coordinates and compare directly with these pre-computed values, reducing redundant calculations and improving efficiency. With pre-processing, the time complexity remains O, m asterisk n, in the worst case because we still loop through all points for each query. However, by pre-computing squared distances, we eliminate repetitive calculations, making the process marginally faster. The space complexity increases slightly to O, n, because we need to store the pre-computed squared distances. Still, this approach doesn't fundamentally reduce the overall complexity. After evaluating these methods, the chosen strategy is an efficient brute force solution. This approach works well because the problem constraints, where both n and m are at most 10,000, are manageable within this framework. By directly calculating squared distances and avoiding unnecessary computations, the solution remains simple, effective, and easy to debug. One key observation is that using the squared distance formula avoids the costly SQRT operation, which would otherwise slow down the algorithm. While more advanced optimizations, such as spatial partitioning with quad trees, could reduce runtime for larger inputs, they would introduce unnecessary complexity and overhead for this problem. Therefore, the brute force method strikes the right balance between simplicity and performance, making it the ideal choice for solving this problem within the given constraints. The problem we're solving here involves determining how many points on a 2D plane fall inside, or on the boundary of, a series of circles defined by given queries. Each query specifies the circle's center coordinates, x_j, y_j, and its radius, r_j. To clarify the input structure, we are given two arrays, points, which is a list of coordinate tuples like x1, y1, x2, y2, and queries, which is a list of tuples specifying the circles, x1, y1, r1, x2, y2, r2. Our goal is to process each query and return an output list where each entry corresponds to the number of points that fall within or on the boundary of the respective query circle. To tackle the problem, the brute force solution provides a straightforward approach. For each circle defined by the queries, we iterate through all the points and use the distance formula to check whether a point falls within the circle. We start by initializing an empty list called results to store the output. For each query, x_j, y_j, r_j, we pre-compute the square of the radius as r_squared equals r_j asterisk r_j, which allows us to avoid redundant calculations. Then, we initialize a counter count to 0. For every point, x_i, y_i, in the list of points, we calculate the squared Euclidean distance to the circle center using the formula, x_i, x_j, caret 2 plus, y_i, y_j, caret 2. If this distance is less than or equal to r_squared, the point is inside the circle, and we increment the counter. After processing all points for the current query, we append the count to the results list. Once all queries are processed, we return the results list as the final output. Analyzing the complexity of this brute force approach, we first consider the time complexity. Let n be the number of points and q the number of queries. For each query, we iterate through all n points, resulting in a total time complexity of O, q*n. This means the runtime scales linearly with the number of queries and points. As for space complexity, the algorithm uses O(1) additional space for computation, apart from the input and output storage. Key optimizations in this approach include using squared distances instead of the Euclidean distance formula, avoiding costly square root operations. Additionally, pre-computing the radius squared for each query minimizes redundant calculations, further enhancing efficiency. Handling edge cases is crucial for ensuring the robustness of our algorithm. One scenario to consider is when the points list is empty. In this case, the result for all queries should be 0 since there are no points to check. Another situation arises when all points lie outside the circle, such as when the radius is very small. Our algorithm should correctly output 0 for such queries as well. In terms of data structures, the input is represented with simple lists, points as a list of coordinate tuples and queries as a list of circle definitions. The output is also a list, where each entry indicates the number of points inside the corresponding query circle. This choice of data structures is effective for the brute force approach since list operations, such as iteration and appending, are computationally efficient and align well with the problem's requirements. For larger inputs, there are optimization strategies that can significantly improve the algorithm's efficiency. One approach is spatial partitioning, where the 2D plane is divided into grid cells. This allows us to focus only on points within nearby cells for each query, reducing unnecessary checks for distant points. Another optimization involves sorting the points by their x-coordinates or y-coordinates. This enables faster elimination of points that are definitely outside the circle, for example, using binary search. In some cases, this can reduce the number of comparisons per query from n to o, sqrt, n, making the solution more scalable for larger datasets. These techniques provide a foundation for enhancing the brute force method in tackling more complex scenarios efficiently. This Python implementation solves LeetCode problem number 1828, queries on number of points inside a circle. The problem requires determining how many points lie inside or on the boundary of a circle for a series of circular queries. The solution is in the countPoints method, which takes two inputs, points, a list of 2D points on the plane, and queries, a list of circular queries where each query specifies a circle's center and radius. Explanation. 1. Initialization. The result list is initialized to store the count of points for each query. 2. Outer loop. The algorithm iterates over each query, xj, yj, rj, where xj and yj are the circle's center coordinates, and rj is the radius. 3. Pre-computation. To optimize calculations, the square of the radius, r_squared, is pre-computed. For inner loop, for each query, the algorithm iterates over all points, 11, e, in the points list. The squared Euclidean distance from the point to the circle center is computed as 11 xj, 2 plus eyj, 2. If this squared distance is less than or equal to r_squared, the point lies inside or on the circle, and the counter count is increment. 5. Result storage. After processing all points for a query, the count is appended to the result list. 6. Return statement. Finally, the result list containing the counts for all queries is returned. This approach ensures that the solution is both correct and easy to follow. Its complexity is O, m*n, where m is the number of queries and n is the number of points. This is due to the nested loops over queries and points, which is acceptable given the constraints. Edge cases, such as no points or queries, are naturally handled because empty input lists will result in an empty result list, which is valid output. Here, we start by importing the necessary utilities and defining our solution class. The main method of interest is countPoints, which will calculate the number of points inside each circle defined by the queries array. First, we initialize an integer array called result to store the count of points for each query. Then, we iterate through each query using a for loop. For each query, we extract the circle's center coordinates, xj and yj, as well as its radius, rj. To optimize our calculation, we pre-compute the square of the radius and store it in r². Inside the outer loop, we use a nested loop to iterate through each point in the points array. For every point, we calculate the differences in the x and y coordinates between the point and the circle's center. Using these differences, we check if the point lies within or on the boundary of the circle by applying the equation of a circle, 11 xj, 2 plus, eyj, 2 less than or equal to or squared. If the condition is true, we increment the count for that query. After counting the points for a specific circle, we store the count in the result array at the corresponding index. Once all queries have been processed, the method returns the result array containing the count of points for each circle. This implementation is straightforward and uses a nested loop to compare each point with each circle. While this approach is simple to understand, its time complexity is O, m*n, where m is the number of queries and n is the number of points, making it suitable for smaller input sizes. With this, the Java implementation is complete, and it efficiently solves the problem by leveraging basic mathematical concepts and iterative logic. In this example, we are given 4 points in 2 queries. We start by initializing an empty list called result to store the count of points inside each circle. For the first query, the circle is centered at 2, 3, with a radius of 1. To simplify calculations, we use the squared radius, which is 1. We then iterate through each point to calculate its squared distance from the circle's center. The squared distance for the first point, 1, 3, is 1, which is less than or equal to the squared radius, so we increment the count. The same applies to the second point, 3, 3, and the fourth point, 2, 2, both of which also fall inside the circle. The third point, 5, 3, has a squared distance of 9, so it lies outside the circle. At the end of this query, we have a count of 3 points inside the circle. After processing the first query, we append the count, which is 3, to our result list. Now, we move on to the second query. This circle is centered at 4, 3, with a radius of 2, meaning the squared radius is 4. Again, we initialize the count to 0 and evaluate each point. The first point, 1, 3, has a squared distance of 9, so it is outside the circle. The second point, 3, 3, has a squared distance of 1, which is less than or equal to 4, so we increment the count. The third point, 5, 3, also has a squared distance of 1 and is inside the circle. However, the fourth point, 2, 2, with a squared distance of 5, lies outside. This leaves us with a count of 2 points inside this circle. We append this count to result, giving a final output of 3, 2 for this example. In this edge case, no points fall inside the circle. Here, we have 2 points in one query. We begin by initializing the result list. For the query, the circle is centered at 5, 5, with a radius of 2, so the squared radius is 4. We set the initial count to 0 and calculate the squared distance for each point. The first point, 10, 10, has a squared distance of 50, which is far greater than 4, so it is outside the circle. Similarly, the second point, 15, 15, has a squared distance of 200, which is also outside the circle. Since no points are found inside the circle, the count remains 0. We append this to result, resulting in a final output of 0. This example introduces a case where points lie exactly on the boundary of the circle. There are 3 points and one query. We start by initializing the result list. The circle for this query is centered at 1, 0, with a radius of 1, which gives a squared radius of 1. We initialize the count to 0 and evaluate each point. The first point, 0, 0, has a squared distance of 1, which is equal to the squared radius, meaning it lies on the boundary of the circle. We increment the count. The second point, 1, 1, also has a squared distance of 1 and is on the boundary, so we increment the count again. Finally, we evaluate the third point, 2, 0, which also has a squared distance of 1. Like the others, this point lies on the boundary of the circle, so we increment the count to 3. After processing all points, we append this count to result. The final output for this query is 3, as all 3 points lie exactly on the boundary of the circle. This concludes the example, highlighting how boundary cases are handled effectively. To analyze the time complexity of this solution, we start by observing that the algorithm processes each query in the queries list. There are m queries, so the outer loop runs m times. For each query, the algorithm iterates over all n points in the points list to determine which points lie inside the circle defined by the query. This is where the inner loop comes into play. For each point, the algorithm calculates the squared distance between the point and the circle's center using the formula 11xj(2 plus eyj(2). This involves basic arithmetic operations, 2 subtractions, 2 multiplications, and 1 addition, all of which are constant time, or O1. Afterward, the squared distance is compared with the circle's squared radius to check if the point lies inside the circle. This comparison is also an O1 operation. Since the inner loop processes n points for each query, it has a time complexity of O(n). Combining the outer and inner loops, the algorithm performs O(n) operations for each of the m queries, resulting in an overall time complexity of O(m*(n). Now, when considering the total complexity, we see that the outer loop runs m times, and within each iteration, the inner loop runs n times. This nested structure gives us a total time complexity of O, m asterisk n. In terms of best, average, and worst-case scenarios, the algorithm's time complexity does not change. Even in the best case, where all points lie outside all circles, the algorithm still checks every point for every query. Similarly, in the worst case, where all points lie inside all circles, the same number of operations is performed. Since the number of operations per query point combination is fixed, the time complexity remains O, m asterisk n, regardless of the input distribution. This makes the algorithm's performance consistent across all cases. Shifting our focus to space complexity, the algorithm uses space primarily for storing the results and a few intermediate variables. The result list, which contains the count of points inside each circle for all m queries, requires O, m, space. Additionally, the algorithm uses a constant amount of space for variables like xj, yj, rj, r_squared, and count during computation. These variables are reused for each query and do not grow with the size of the input, making their space usage O1. The input points in queries lists are read-only and do not contribute to additional space requirements since they are already provided as input. Combining these factors, the total space complexity is dominated by the result list, which is O, m. No additional space is used beyond this, making the overall space complexity efficient. Comparing the current solution to potential optimizations, it becomes clear that this approach is essentially a brute force method. It explicitly checks every point for every query without leveraging any spatial optimizations. While this method has a time complexity of O, m asterisk n, the same as a general brute force approach, it does not utilize techniques like spatial partitioning or preprocessing. For example, using a quad tree or KD tree could allow the algorithm to narrow down the points to consider for each query, reducing the number of distance checks. However, these optimizations would introduce pre-processing costs and are not part of this solution. From a mathematical perspective, the total number of operations is determined by the product of m queries and n points, which dominates any lower-order terms. Thus, the time complexity remains O, m asterisk n. Meanwhile, the space complexity stays O, m, as the result list accounts for the primary space usage. Together, these complexities summarize the algorithm's performance and potential areas for future improvement. When solving this problem, there are several common mistakes to watch out for. First, not pre-computing repetitive calculations can significantly slow down your solution. For example, recalculating the squared distance formula repeatedly for the same query is inefficient. Instead, consider pre-computing or optimizing these calculations to save runtime. Another issue is incorrectly handling boundary conditions. If a point lies exactly on the circle's boundary, you must explicitly decide whether the problem considers it inside the circle or not, as this can lead to incorrect results. A third mistake is relying on a brute force approach for large inputs. While checking every point for every query might seem straightforward, this O, n asterisk m, approach becomes impractical for large datasets. Finally, mishandling floating point precision is another common pitfall. For problems involving floating point coordinates or radii, direct comparisons can lead to inaccuracies. To avoid this, use integer math, such as squared distances, to maintain precision and ensure correctness. Now, let's talk about edge cases and interview insights. Overlooking edge cases, such as queries with zero radius, overlapping or concentric circles, or scenarios where no points are provided, can lead to unexpected failures. It's essential to account for these possibilities in your solution. From an interview perspective, this problem belongs to the category of geometry-based problems and range queries. Recognizing this can help you identify optimization strategies, such as using quad trees, KD trees, or spatial hashing, instead of brute force. It's also important to clarify assumptions about the input, like the maximum number of points, queries, and coordinate ranges. This information helps you gauge whether advanced optimizations are necessary. Additionally, interviewers appreciate when candidates discuss trade-offs, such as the time invested in pre-processing versus the speed of queries. For instance, while building a KD tree takes O, n log n, it significantly improves query time to O, log n. Even if you don't implement these advanced techniques, demonstrating an understanding of spatial indexing or divide and conquer strategies can leave a strong impression. This problem has connections to other geometry-related challenges that can help you build a deeper understanding of spatial reasoning. For example, LeetCode 223, rectangle area, is another geometry-based problem that requires careful boundary condition handling, similar to the circle queries in this problem. LeetCode 850, rectangle area 2, involves optimizing for overlapping areas, which also emphasizes spatial reasoning skills. Additionally, LeetCode 1272, remove interval, is a range-based problem that highlights the importance of handling edge cases in optimization. By exploring these related problems, you can practice key techniques and strengthen your ability to approach geometry and range-based questions effectively. Finally, let's review some alternative approaches to solving this problem. The brute force approach involves checking every point against every query, with a complexity of O(n*(m). This method is straightforward and requires no pre-processing, but it's highly inefficient for large datasets. A more efficient option is grid-based bucketing, where the space is divided into a grid and points are assigned to specific cells. For each query, you only check points within the circle and its neighboring cells. While this can be faster, tuning the grid size is critical to balance pre-processing and query time. KD trees or quad trees offer another advanced solution. These spatial indices divide points into hierarchical regions, reducing query time to O log n after an O and log n pre-processing step. Though efficient, they are more complex to implement. Lastly, spatial hashing maps points to buckets based on their coordinates, and you only query adjacent buckets to find points within a circle. This method works well for uniformly distributed points but may suffer from collisions if the data is skewed. Each approach has trade-offs, and the choice depends on the problem constraints and input size. Great work! To recap, we tackled the problem queries on number of points inside a circle using a brute force approach. We emphasized the importance of understanding geometric relationships and analyzing edge cases. Remember, practice makes perfect. Keep solving problems to sharpen your skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!